Okay, we're back. Now I want you to, I'll get to this picture in a second. I want you to remember something I said in the first video, which is when you're laying there on the flat Earth, it's not really flat, just thought I'd let you know. In case you're curious, spherical. So, you're laying there on the Earth with a nice horizon view, the dark sky, and you had 3,000 stars above you. I mentioned there's also 3,000 stars below you. There are stars down beneath us as well as overhead. So if you think of the Earth as a sphere, it's very useful, not true, but it's useful to imagine, and for thousands of years people thought this was true, that all the stars are painted on a great, big, ginormous sphere that's centered on the Earth. This is the Earth. It was believed that there was a sphere that was thousands and thousands and thousands of times larger than the Earth itself, and all the stars were kind of painted on, sort of, with glow-in-the-dark paint on the inside of this big sphere. Okay, so all the stars in their imaginations and in your imagination at this moment, imagine that all those stars are painted onto a big sphere that wraps not only over your head but goes under your feet as well. It's like the Earth curves down and around from you and meets at a point below your feet. So does the sky surround you and meet at a point down below your feet. Okay? So the Earth sometimes is known as the terrestrial sphere, right? Well, that big ball of the stars painted on the inside of it is referred to as the celestial sphere. So let's look at the drawing now. Let's focus on the Earth part, a little part here in the middle. There's some features of the Earth that you're familiar with, right? You've got the North Pole here. You've got the South Pole here, right? And you've got the equator. Actually, let me draw that on the other side. I need the space on this side. So you got the equator, right? The line that wraps around the Earth halfway between the two poles, right? So there you go. There's the Earth, the Earth sphere. Now, there's something else. I don't know if you're familiar, but the city of, let me back up. You know what latitude and longitude is on Earth. Latitude and longitude on Earth tells you where we are on the Earth. For example, right now at Agnes, let's see, at Agnes Scott College, where I am right now, latitude is about 34 degrees north, and longitude is about 80, I think it's 85, 84 degrees west. So if you pull out your phone and pull out your compass on your phone, it'll say, if you're here where I am, 34. It's got some arc minutes and arc seconds in there too, but 34 degrees north, 84 degrees west. Of what? Right? In other words, there's a grid on the Earth that locates every point on there. Every point on the Earth has two numbers, right? It's got a latitude and a longitude that tells you where on Earth it is. Whether it's in the ocean or whether it's on the land or it's the North Pole, South Pole, wherever, there's a set of two numbers, latitude and longitude, that tells you where on the planet that thing is located. Okay. Well, it turns out that if you draw a line, the question is with reference to what? 34 degrees north of what? 84 degrees west of what? I'm going to answer that question. If you draw a line, okay, from the North Pole to the South Pole through Greenwich, England, you could have done it anywhere, but historically that's where it's been done. The Greenwich, England, you have a line that goes something like this, right? Now that line, I'm not going to write it on the picture because it's going to be too complicated, is known as the prime meridian. Okay? The prime meridian runs from the North Pole to the South Pole and goes through Greenwich, England, where there's a very famous historical observatory. You can go and stand there on the prime meridian. It's kind of fun. And where that prime meridian crosses the equator, that is the point relative to which we are 34 degrees north of that point and 84 degrees west of that point. Okay? So that's the Earth. Okay? That point has a name. I can't remember what it is. It's not important. The pink line is the prime meridian. Okay? Again, I'm not going to write that on the picture because it's going to jumble it up too much. So those are the relative points on the terrestrial sphere. Now what we can do is to project these points and lines out onto the celestial sphere. So if we keep drawing this line up, okay, there's a point up here, right, where the line comes out of the celestial sphere, and down here there's a point that it goes through. All right. So we've got the North Pole here, top of the Earth. Directly above that is the North Celestial Pole. So you go up to the North Pole and look straight overhead, you'll be looking at the North Celestial Pole. Right? Now, if we trek down to the South Pole, our heads will be pointed down in the picture here, and right over our heads will be the South Celestial Pole. So we have the North Pole and South Pole on the Earth, and then connected with those on the celestial poles, the North Celestial Pole, on the celestial sphere, is the North Celestial Pole and the South Celestial Pole. And these are simply points on that big ball of stars. It happens to be the point on that big ball of stars which is directly above the North Pole, and the South Celestial Pole happens to be that point on the big ball of stars which is directly above or beneath, as the picture shows here, the South Pole. Okay? And there, so we have the celestial poles. We also have a celestial equator. Okay, which I'm going to draw right through the SP there. And it goes back around the back like this. Okay, so what we have here is a nice big sphere with the North Pole, a South Pole, and then we have the celestial equator, which is a big circle that goes all the way around the celestial sphere, and it's sort of an outward projection of the terrestrial equator, which we just call the equator. So in other words, there are matching points for the poles, and there's a matching circle for the equator, matching on the terrestrial sphere and on the celestial sphere. Okay. And there is also there's a latitude and longitude grid set here. You know, the grid on the planet. We also have a grid that we can imagine on the celestial sphere, with also two numbers that indicate any particular location on that sphere. Okay. Now, I want you to realize that the stars, okay, on the sphere, for our money, for now, don't move around the sphere. They stay stuck on it, just like towns and cities stay stuck on the terrestrial sphere. Like Atlanta's longitude and latitude does not change over time. Or the Earth is rotating, but the grid rotates with it. So latitude and longitude of Atlanta stays the same all the time. Atlanta's not on wheels. It doesn't move all around the place, right? Like when you get in the car and drive somewhere, your latitude and longitude change as you move across the grid. Stars are like cities. Their latitude and longitude don't change. Okay? So in the same way that there's a grid of latitude and longitude on the Earth, there's a grid of latitude and longitude on the celestial sphere, but it's not called latitude and longitude. Okay? It's called right ascension. See if I got that into the, yes, it fits in the video. Right ascension, okay, that's like is kind of like latitude. I'm sorry, light ascension is sort of the equivalent of longitude. It's the same concept, just with different names. Light ascension, it's like longitude. And the equivalent of declination, the equivalent of latitude is called declination. That is like latitude. Okay. So in the same way that Agnes Scott College has a latitude and longitude, any given star will have a right ascension and a declination. And we shorten these often to RA and dec. And this is a grid that's out on the celestial sphere. So Agnes Scott is at these coordinates of latitude and longitude. Let's look at our star Betelgeuse that we looked at a few minutes ago and see what its coordinates are. This pink pen is disappointing me. It is drying out. So let's try a different one here. Star Betelgeuse has its coordinates as well. Okay. Right ascension and declination. And that locates the star on the celestial sphere in exactly the same way that latitude and longitude locate a city or a town or a college on the terrestrial sphere. Now what I'm going to do is I'm going to give you the coordinates of Betelgeuse, and I'm going to explain them. We're going to do dec first, the declination. The declination of Betelgeuse is plus 7 degrees, 24 arc minutes. Okay. Right ascension of Betelgeuse, get ready for it, get ready for it. The units are different. For Betelgeuse, the right ascension is 5 hours and 55 minutes. 5H, 55M. The units for declination are in units the units of right ascension are in hours. I'll show you how that works. Okay. The issue here is these are relative to what? These are, whatever these numbers mean, they have to be measured relative to something. They're measured relative to a point out here on the celestial sphere, given by the symbol of Aries. Aries symbol means the vernal equinox. Don't have to worry about what vernal equinox means right now. For our money, it's simply a point on the celestial sphere. Okay. And so here's how these locations work. Let's draw Betelgeuse on the map, on the ball here. Let's draw it back here. Now this is going to be back on the back side. Okay. So what this 5 hours and 55 minutes means, that tells you the location around the celestial sphere. Instead of breaking up the celestial equator into 365 degrees, it's broken up into 24 hours. So right ascension runs between 0 and 24 hours. The vernal equinox is at 0. So if we move this direction around the equator, we have to move 5 hours. We have to move, this is the 0 hour mark. We have to move backwards around this way to the 5 hour 55 minute mark, and then we have to move up. This is 7 degrees 24 arc minutes. And this arc here going back to the back of the celestial sphere, this goes to 5 hours and 55 minutes. So if you imagine the whole equator being 24 hours around, we only have to go, maybe a fourth of the way around to get to 5 hours and 55 minutes. Okay, about a fourth of the way around. And then up from the equator 7 degrees 24 arc minutes. And this is plus because we're going toward the north. There's another star that I mentioned a few minutes ago down here. This is Alpha Centauri. To get to it, we have to go further around. We have to go, let me see, Alpha Centauri is at 14 hours, 39 minutes. We have to go all the way around, back like this, and down here to about here. This is 14 hours out of 24, 14 hours and 39 minutes. And then we have to go down 60 degrees, 50 arc minutes. Okay. So the right ascension tells you how far around the celestial equator you have to go to get to that star, and then the declination tells you how far above or below the celestial equator you have to go to get to that star. The idea is exactly the same as latitude and longitude, just with a different name, right ascension, declination, okay, and with different units for right ascension. It's in hours and minutes, not arc minutes, okay, hours and minutes, not minutes, arc seconds, it's hours and minutes. So 24 hours around, there's a reason for that, 24 hours around the celestial equator, and then you can go from 0 to 90 degrees to the north and from 0 to 90 degrees from the south for your declination. We'll do more of this, and you'll have plenty of chances to practice this in your labs. So that's it for this lecture. We will start up again tomorrow. See you then.